Now we're in the final section, and it's all examples. And be superb if you went through all of those examples in detail, and actually you'll find that those examples are pretty closely related to examples we've already done in class. So the only one that isn't one that we've done in class is challenge example 6.11. So let's take a look at challenge example 6.11. Here's some kind of box, and here's some kind of surface, and here's somebody's hand, and they're going to push, actually they're going to grab and push and pull on this box. Okay, so they are going to push and pull. And we're going to have a kind of complicated expression for how hard they're going to push and pull. The expression for how hard they're pushing and pulling, they're going to push and pull in the x, the horizontal direction, and fx of t is going to be some constant c times sine of pi t, the time, over capital T. That's the way Knight wrote it. Capital T here represents a half of a period rather than the usual whole period. Let's write the free body diagram for this situation. We have three things. We have a normal force up. We have Fg down. And we have this, say, F hand to the right. And the amount that F hand points to the right is Fx of t, which is that expression. And actually, this expression can go negative. So when Fx of t goes negative, actually F hand points the other way. But I'm going to draw F hand as pointing right, and then you'll know that whenever this becomes negative, that happens, for example, when this entire argument here is between pi and 2 pi, this goes negative. Now let's analyze that free body diagram by breaking it into components. You have a normal force. First I'll do the y component. You have a normal force n in the upward direction, and you have mg in the downward direction. Now the way I drew the picture, this box is just sliding back and forth along this surface, and this surface doesn't have hills in it, and it doesn't have ditches in it, so the y position is always the same. So there's no acceleration in the y direction. So we have n minus mg is 0. And actually, since this force of the hand doesn't depend on anything, it's just given, this equation doesn't really tell us anything interesting in this problem. Now let's do the x component of F equals ma. The x component of F equals ma, well, there's only one force in the horizontal direction, and that's this Fx of t. And that's going to be equal to ma. Well, that clearly means that a is itself a function of t. We've done a lot of problems where a is a constant. In this problem, the acceleration a is variable. And now we can solve for it by plugging this into here and dividing through by m. We get that a of t is equal to fx of t over m, which is equal to c over m sine pi t over t. So now I've graphed it, and the coefficient is c over m. So this thing goes as high as plus c over m. The sine function goes from plus 1 to minus 1, so down here we're at minus c over m. Now you know what the sine looks like, but the question is when does it cross the t-axis here? Well, if you plug in little t equals big T, then you get sine of pi. And that's the first 0 of the sine function. It goes up, and then it crashes back into 0 when little t equals big T. And then if you put in little t equals 2t, well, then you've got sine of 2 big T times pi over big T, which is sine of 2 pi. That's the second 0 of the sine function. So I've drawn this correctly. There's a 0 at, well, there's one at 0, and then there's the first one away from 0 is at capital T. The second one is at 2 capital T. The third 0 is at 3 capital T. And it just continues on like that. Let's add a little bit more information to this problem so that we can compute a little more. Let's assume that at t equals 0, Vx of t is 0. Okay, nice simple situation. I'm going to start off with 0 velocity. Well, that means that you can find Vx at any later time t by using that area under the curve business. We know we can get the change in the velocity by getting the area under the acceleration curve. Now, since it started at 0, the change in the velocity, Vx of t minus Vx at t equals 0, that just simplifies to Vx of t. So Vx of t is equal to the area under this curve between 0 and t. And in this zone, the area is building up as time increases, but then because we count acceleration below the x-axis as negative area, here the velocity must be decreasing. And here, in this zone, it's increasing again. It's a very interesting special case which we'll go way deeper into later in the semester. It's called oscillatory motion.